The elements. It's our next chapter. So let's look at metals. The elements are separated as metals, non-metals, and metalloids. Right? So most elements on the periodic table are actually made up of metals. Most are shiny and silver or gray in color. So if you looked at each one of these elements, that's the property that they're going to exhibit. Okay. They are excellent conductors of heat and electricity. And they're all malleable and ductile. Malleable means to bend. You should already know that based back on the properties of matter, right? One of the physical properties is the ability to bend something, right? So metals can bend, right? You heat them, and allow you to bend some. You can actually bend without having to heat them at a room temperature. Ductile means, can you stretch them out into a wire, just like copper, right? You can copper wire, stretched out copper into wire form. Okay, and these are properties of metals, right? Most of the elements are metals, and these are their properties. Non-metals. Only 17 of the elements found in the periodic table are actually considered non-metals. Okay, they are grouped together because they do not resemble metals whatsoever. So if you look at something called the aluminum ladder, you'll see something that looks like a staircase on the periodic table. That staircase separates the metals from the non-metals. So in the periodic table, you'll see something that looks like this on the periodic table, right? And the first step here up at the top is that of aluminum. That's why I call this the aluminum staircase. The elements found on this side are the metals. Right? Most of them are metals, as we said. The atoms on this side are known as the non-metals. Some of the elements that lie along this aluminum staircase are known as the metalloids, as we're going to see in just a second. Now, in terms of these non-metals, 11 of the non-metals are gases, okay, and that's the state of matter that they're in when they're at room temperature. I'm not going to go through which ones are, okay? You can always look that up. 5 of them are solids. Again, you don't need to memorize these things, okay? One of them is actually liquid, and that's the only one that I do want you to know, is the fact that bromine, of all the non-metals, bromine is the only one that is in liquid form at room temperature. Metalloids. The remaining elements are called metalloids. So notice the name metal in the word metalloids, right? So they exhibit properties that are similar in both of metals and non-metal properties, right? So metalloids conduct electricity, but not very well, right? That's why they're called semiconductors, because they semi-conduct electricity, right? They can control the flow of electricity, and that's why they're often used in electronic devices like computers and such, right? Because they control the current, the electrical current. So here's a periodic table. Here's the aluminum ladder, as I showed you guys, right around aluminum. So metals on this side, non-metals on this side, right? With these ones here being, okay, the metalloids, right? And they exhibit properties that are similar. That's why we put them kind of on the fence here, right? They're on the fence here on either side because they exhibit some metallic, some non-metallic properties. By the way, you will not be asked to memorize this, but if you go on YouTube, you can find actually a little kid who can actually recite all these elements. Which I thought was pretty cool when I saw it. So, some physical properties of metals, non-metals, and metalloids. So the state in which metals are in, they're solid at room temperature, except for mercury. So here I'm always going to show the odd one. So the only metal that is not a solid at room temperature is mercury. And that's why they're great tools for as thermometers, right? Because they're liquid at room temperature, right? If you're measuring something, measuring the temperature of something, right? Using a mercury thermometer. The appearance. They're shiny luster, as we said. They're silver, gray, right? But they're shiny. Conductivity. Well, they're good conductors of heat and electricity, right? So they allow current to flow. They get very hot, right? Think about if you're, stirring a hot pot, right? You wouldn't want to stir it with bare hands with a metal spoon, because that metal spoon will get hot. It conducts heat, right? So you'd want to use a wooden spoon, which doesn't conduct heat. And malleability and ductility, yes, they're both malleable and ductile. Nonmetals, there are some that are gases at room temperature, some are solids, only one of them, being bromine, being the only liquid nonmetal. Their appearance, not very shiny, oftentimes very dull. Okay. They are poor conductors of heat and electricity, so they not be used, okay, to allow the flow of a current. In terms of malleability and ductility, they are very brittle, right? So if you would try to bend them, they will probably crack, right? So imagine like a piece of glass, right? Trying to bend glass, right? You bend glass, you can't, right? Unless you really you heat it. But we're looking at something completely different here. But if you try to bend it, just as is, it'll shatter. So think of that kind of a property for nonmetals. Okay? And metalloids, solids at room temperature. They can be shiny, cannot be. It all depends, right? Metalloids, remember as we said, exhibit properties similar to both metals, nonmetals. May conduct electricity, but they're poor conductors of heat. Okay? As we said, may conduct electricity, semiconductors. They somewhat allow it, right? And they control the flow of electricity. They're brittle and also not ductile. Very similar. So here's the non-metallic property that these metalloids actually exhibit. So let's look at a few common elements of the periodic table. Iron, quite common, right? Very strong, and if we combine it with carbon, okay, we can make steel. That's how steel is made up, right? Steel is even stronger than iron, right? So we combine iron with carbon, form steel. Make that iron even stronger than it already is. Steel can be made fairly resistant to corrosion. Plain iron corrodes easily in moist air, forming an orange compound called rust. As we've said in the previous chapters, rust is a chemical change. Right? Chemical changes are irreversible or very hard to reverse. Right? You see rust in the car, that's it. You know, that's it. It's slowly eating away. That's irreversible. Right? You can't get that, metal body back to its that part back to its original self without having to replace it. Carbon exists in several forms, including graphite and diamond. Okay, graphite found in your pencils, right? It's not lead that's found in pencils. No longer lead. It's actually graphite. A lot safer. Coal, a form of graphite, is a black solid made mostly of carbon. Right? People use coal. If we think of the Industrial Revolution back in the 1700s, they discovered that we can actually heat for a longer period of time using coal, right? But coal that's mined and burned, okay, helps produce heat. The only thing is that burning of that coal, right, which helps generate electricity, is actually destroying, let's say, is adding to the greenhouse, right? It's a greenhouse gas, right? And it's pretty much adding to the pollution that we're finding all over the world. So burning of coal produces air pollution, major contributor of greenhouse gases in the atmosphere that's now causing this global warming that we're hearing so much about, right? And that these gases affect our climate. Yeah, they're great to heat a home, right? But again, they give off too much of these greenhouse gases, and that kind of relates to the ecology and climate change unit. Hydrogen. Hydrogen is the most common element in the universe. In fact, it's even beyond. So within our universe, it's within our solar system. In fact, right? We can find hydrogen in even some of these planets, right? So it makes up most of the atoms in stars as well as large planets like Jupiter and Saturn. Okay, we talked about the idea of hydrogen fusion in the Earth and Space Science unit that we just covered. It's the simplest and lightest of all the atoms. So if you look at the periodic table, the very first element on the periodic table is hydrogen. The first element, the lightest element. At the center of all stars, hydrogen atoms combine to form atoms of even other elements through nuclear reactions. Right? But don't worry about that. That's, again, more on a senior chemistry level. Okay, but know that most common element. Right? We find it even in water, hydrogen. Right? We find hydrogen in sugar. Right? We find hydrogen almost everywhere we go. Right? So anything that's considered what we call a hydrocarbon, made up of hydrogens and the carbons, as we saw in the previous slide. On Earth, almost all the hydrogen that is present is in the form of water. Right? Remember, majority of the planet, our planet, is made up of water. Right? H2O. Remember, H2O, law of definite proportion. 2 hydrogens, 1 oxygen. Right? Pure hydrogen gas is colorless and odorless, and it's lighter than air. Right? We can use it to inflate a balloon and cause the balloon to pretty much float in the air, just like those helium balloons. Right? The only thing is, as we're going to see, it's extremely flammable. So you're at a party, you fill the balloons up with hydrogen, someone's smoking in the room. They'll all explosively pop. Right? So even though hydrogen is the lightest one, we're not going to use hydrogen to inflate balloons. We can. Right? Right? We think about the Hindenburg. If you research the Hindenburg and then why it went down, it's made up of hydrogen. Right? And it exploded. Because hydrogen is very explosive. Oxygen makes up about 21% of the air we breathe, and our bodies need a constant supply of oxygen to survive. Right? So it's in the air around us, but believe it or not, it's not that much. Right? 100% of the air, only 21% is actually oxygen. The other part, almost 80%, is actually nitrogen. The oxygen gas that we breathe is in the form of 2 oxygen atoms bonded to one another in the form of what we call O2. So when we see O2, we refer to oxygen gas. Most of the oxygen gas in Earth's atmosphere comes from plants and algae which produce oxygen while using sunlight to make sugar. This is the process called photosynthesis. So we need plants, right? Tearing down the rainforests, cutting down trees, right? Paving, fields, open fields into cement playgrounds, right? Into malls. We are removing oxygen from our atmosphere because the grass, the trees, the bushes, all these plant type organisms, they produce oxygen through photosynthesis that give us the oxygen that our bodies need. Ozone, right? When you hear about the ozone layer, helps pretty much absorb some of the harmful ultraviolet radiation, right, that is exhibited from the sun, right, outside of our atmosphere, right? Ozone, pure oxygen, in which 3 oxygen atoms are actually bonded together, right? You wouldn't want to, breathe this in, but it's very far away from us. That it's actually useful as a tool to absorb these harmful ultraviolet rays. Right? There was a time when we were really worried about the depletion of the ozone layer. Right? And because of changes we've done here on the planet, we've been able to allow the ozone layer to replenish itself, right, to a certain degree. Right? Because remember, harmful UV rays are cancer causing. Oxygen is the most common element on the Earth's surface as well. So it's not just a gas, okay, in our atmosphere, in the air, okay, but it also makes up part of the Earth's surface. Oxygen makes up more than 50% of the mass of most rocks. So believe it or not, the rocks made up of great portion of oxygen, because what it does is it bonds with this other nonmetal called silicon. When certain kinds of rocks are grounded up, they become sand, which can melt and harden to form glass. Most of the atoms in glass are oxygen atoms, believe it or not. So here is a look at the percentage composition of the atmosphere. So we're looking at dry air, right? And here's where oxygen lies, about close to 21%. 78%, depending on the book, sometimes they might say 80%, right? But between 78 to 80% of the air around us is actually made up of nitrogen, right? And we look at this, the carbon dioxide levels, CO2, look at how small percentage that is. That's what we breathe out. Right? That's what plants need during photosynthesis with the combination of water and sunlight. But because of the pollution that we're adding to it, this level is actually increasing. This increase in carbon dioxide is what we're calling the increase of these greenhouse gases. Right? We think about what a greenhouse does. It traps heat in. That's what we're doing. By increasing the greenhouse gases in our atmosphere, we are able to trap in more heat. When you come, when you live in a city like we do in Toronto, it gets pretty cold, right, in the wintertime. So we're thinking, hey, that's great. But this increase in greenhouse gas, as we're noticing, is actually causing a great deal of catastrophes around the world, right? That so-called global warming. The planet is warming up because the greenhouse gases are trapping in that heat. Okay, a few notes to keep in mind: neon, helium, krypton, and xenon are also found in dry air, but really, really tiny amounts that really don't make a difference to put in a table like this, but that they do exist. But you do not need to memorize it. If anything, remember the fact that nitrogen, about 78 to 80%, and oxygen, 20, 21% of the air is made up of those two gases. Three of the gases, nitrogen, carbon, and carbon dioxide, go through cycles that are essential to life on the planet. So even though we said carbon dioxide is a bad thing, right? A certain amount, yeah, it's good. We need it, right? Plants need it, as we said, to allow them to undergo photosynthesis. But we don't want that percentage to go up anymore. Right? That's really what, if we're looking at it on an ecological point of view, right? Being green, right? Going green and doing things green, right? We're trying to keep the levels at the level that is naturally recycled on the planet. Oxygen is so reactive that it cannot exist for more than an instant as an uncombined atom. So we look at oxygen as just O, but it is bonded to another O to form the oxygen gas as we know as O2. So you'll never find just O by itself. This O always wants to bond really quickly because it doesn't exist for very long on its own. Right? And you're going to find, we're going to talk about other atoms that actually exhibit the same things, like hydrogen, another one. It will never exist as itself. It will immediately bond with another hydrogen. But don't worry about that. You don't need to know that right now. The oxygen in the atmosphere is therefore in the form of a diatomic molecule of O2. Diatomic, di meaning two atoms. Two atoms of oxygen form this one molecule. The nitrogen gas in the atmosphere consists as an N2 molecule. Also, because it's N2, it's also considered diatomic. So, when we look at this diatomic, di meaning two atoms, the atoms are always going to be the same. So it's N2. We look at something like H2O. Even though we see this 2 with H, it's not diatomic here because there's an O with it. But if we look at hydrogen on its own as just H, here is hydrogen gas. This is H2. This is diatomic because it's got two of the same atom only. So argon is unreactive and is not involved in a cycle. So of all those that I showed you guys in that table, argon is the only one that actually doesn't, it actually exists on its own. It doesn't bond, and you'll see that when we talk about what we call noble gases. They're what we call at a stable state. Okay, and they're very unreactive. Okay, in fact, all those elements on that side of the periodic table, in that column or group, okay, are considered unreactive. But we'll talk about that later. So, Earth, elements in the crust. Earth's crust is our planet's outermost layer of solid rock. So, in this, we show pretty much some of the principal elements. Notice here, majority of the Earth's outer layer, right, Earth's crust, is actually made up of oxygen. Next, most abundant non-metal, silicon. Together they form the rock, the sand. Okay? And then we have other things like aluminum and iron, but don't worry about those ones. But do know the fact that the majority of the Earth's surface is made up of oxygen and silicon. And we'll see a little more about that in a second. Now, notice that most abundant element is oxygen. But how can it be, right? We're talking about a solid. We know oxygen is a gas of all things, right? So how is that oxygen now the most abundant element? And as we said, oxygen is very reactive. All right? Oxygen atoms are very reactive. When one atom of oxygen combines with a second atom, the result is oxygen gas. But in fact, not just that, right? It actually bonds with others, right? Remember, silicon is the other one, right? But many other elements are also reactive. Oxygen combines with silicon, as we said, the second most abundant element on the Earth's crust, and it forms silicon dioxide, SiO2, right? And that forms pretty much sand. That forms sand. Oxygen combines with the element iron, right? Iron that can also be found, and that forms rust. So notice how reactive oxygen is. Even though oxygen at room temperature is a gas, but oxygen alone is very reactive, that it reacts with other elements to form new compounds. And these new compounds also have oxygen within them. So oxygen can exist as the gas, as O2 gas that we breathe in. Oxygen can exist in sand. Right? Sand is used to help make glass. Right? We talked about sugar, C6H12O6. Right? Here's the formula of glucose. Right? Glucose. We said hydrogen, most abundant element on the planet, in the universe, in fact. Right? It's found there in glucose. Look what else is found in glucose. Oxygen atoms. Okay? Oxygen is very reactive. Hydrogen, very reactive. How strong an element reacts is an important chemical property which helps us understand reactivity. Right? So how reactive is an atom? That's really important to know, because we want to know how stable is this atom alone. Is this going to react and form a new compound? Maybe this new compound might be actually harmful. Right? So we want to know reactivity. So let's look at a couple of atoms. Sodium metal reacts immediately and violently if it's in contact with air or water. Look up on YouTube. You'll find a couple of videos where they place sodium into water and you watch it react. Right? As you look at these things, you're going to see, we're going to talk about these atoms. Right? Sodium is considered an alkaline metal. All alkaline metals react violently when exposed to air and water. Now, if you look at sodium in the periodic table and you keep moving down, it becomes more and more reactive as you go down that group, but we'll talk about that later. Pure sodium metal is usually stored in oil, where it can remain without reacting for a long period of time, right? It's reactive with water, but remember, oil and water don't mix. Right? So if you store it in oil, it keeps it unreactive. Right? Sodium metal is very soft metal. So if you had sodium metal, you could cut it pretty much with a knife very easily. Sodium commonly exists in compounds such as table salt, which it forms with the element chlorine, right? Forming sodium chloride. So you look at the table salt, this is the formula for table salt, NaCl. That is the name, the chemical name for table salt, sodium chloride. Sodium itself, very corrosive, very reactive, right? But notice, you combine it with another reactive element, and you actually form something that is actually edible, something that helps make fries taste so good. Right? Chlorine. This one is a nonmetal, yellow-green gas at room temperature. High concentrations of chlorine gas are toxic and will quickly destroy lung tissue if you breathe it in. Right? But you combine it with sodium, you make something that is edible. Right? At lower concentrations, another purpose of chlorine, it's useful as a disinfectant. Right? We use chlorine in swimming pools and community water supplies to help kill bacteria and other organisms that can actually spread disease. So in low concentrations, it's good. High concentration of it, bad, toxic.